So, any questions from last class? Okay, so today I will again I'll do the coding for this coding of this Hoffman code problem using the same heap data structure. Uh, Before that, I would like to discuss. Yes, any question? Yes. Okay, so in the last class, I have discussed a little bit about this malloc and calloc, and someone asked me about the difference between these two. And I explained with some handwritten example. I will do coding for that one too first. So in today's class, first I will do the coding for this. I mean, I will demonstrate an use of this malloc and calloc, and what is the difference, like what is the main difference between them. And like you will see, you can see that in the code. And after that, I will write the code for the Hoffman coding problem. And I will be using this heap data structure. There are other ways to like tackle this Hoffman code also. Without using heap, you can implement it without using heap. Where I mean, like I am using this heap to maintain the structure of that sorted array. That sorted array, I mean, in Hoffman code, if you remember that we sort these numbers, sort these characters based on their frequencies, and we maintain an array of these frequencies, and we always choose the two minimum frequencies and make them two leaf nodes of the tree, of the Hoffman tree. Uh, this okay, so now when we do that, when we make this two smallest frequencies to be the leaf nodes, what we do in Hoffman code is that we introduce another node, which is the sum, which actually takes the sum, which actually contains the sum of these two frequencies. And these two frequencies become the children of that node. Okay, so that node is and like so, and what we do is that we insert this node again inside the array. Okay, and again we take the small frequency, we keep on repeating this step. So this like when we insert again, in the array to maintain the sorted ordering or like picking up the minimum values. This heap property is very useful, okay, because we can manipulate these heaps in order log n time. If you can see, I mean, you if you read heap, you'll see that insertion or deletion in heap can be done in deletion. I mean, after deletion, you have to modify, because deletion means you just take the root, but that's not the case. You have to modify the tree to make it heap heap also. So this insertion, deletion, this operation takes order log n time in heap. So uh, and so every time when we are operating, like when we are inserting one frequency in there, we can maintain this structure in order log n time. So the time complexity reduces a bit. Otherwise, like if every time you have to use another any other sorting algorithm, okay, to sort the array that are going to be like inserted in there. So it will take a little bit, little bit more time. So the better structure is heap. That's why we are using this heap node. Heap to maintain that sorted array. Okay. So first, now I will do the code for malloc, and you will see the difference between malloc and malloc. So, uh, so for example, mm, mm, so I hope that you guys are comfortable with C++. Uh, I mean, like you said that C++ is okay. I think you guys are more comfortable in C++ than C, I guess. So I'm following C++. So I am just using this. I'm not going to describe like what are the syntaxes. I just demonstrate the use of this malloc and calloc. So to use malloc and calloc, you have to include this standard library in there. It allows you to use this function. Okay. So I'm creating a pointer. Uh, that if you remember, this was the structure, right? Name of the pointer, or like the variable that you wanted to point, and then the type of the variable, then malloc and size of that site. This was the format, if you recall. So this is the way to define. So I have defined this star PTR here. I mean this PTR. So it's an integer pointer, and what it does is that it allocates some memory. Okay. So if you write, if we are assigning 5 in here in the allocated memory, and if you perform cout, do that, you will for safety returns. So if you compile this one, you'll get the value of that stored in the allocated memory, right? Okay, so this is your malloc. Also, like you can check that also like if you want to add some spaces, I mean, like what I said is that if there is a format like size into something, so you can allocate like number of blocks also. Okay, some I mean, let's say you want to add 6 blocks. Okay, so what it does is that it allocates 6 blocks of memory corresponding to this PTR. Okay, so how you can check? You can run a loop. Okay, let me just remove this one. Now you can enter this enter values in this pointer at like each position. So for less than 6. It's a similar for loop that you have seen in C. It has the same structure. So, yeah, here I have initialized some values so that if when it prints, because malloc does not initialize any value, so when it prints, it will print the these values. So you can check that there are values at that position. Count, it's not count, it's see out. See out. You have written count. So it did not read the command. It should be see out or std double colon see out. That since you are using namespace, so it's just see out. If you are using namespace, you have to use see out only. Otherwise, you have to use like standard std. Yes, it's the character output. It's included in this standard namespace. So if you are not using namespace, you have to write like std double colon c out. Okay, that's the format. All right. Uh, let's move on to this. Okay, so I have initialized, now I have to print. Right. Um, so I want to print this. So there is a one form I have written here. It's in the form of array. You can also interpret it in this way. Both performs the same thing. Okay, and it's endl. And after that, if you recall, I always say that free the memory that are allocated in malloc. So let's run this one. Okay. So see, okay. So I have stored some values in there. It's just even numbers, and it gives the output as these even numbers. These values are stored in there. Okay. So this is the more or less use of this malloc. I can define arrays. I mean, the block of memories, not arrays. Should not say like that. It's a block of memories that I can allocate. Okay. Now, another example. Now we give an example of this calloc. Okay. So you saw that calloc has like two. Just change this one. Two arguments. So I'll just change the name and the arguments. I'll make this, and I will not do the initialization in here. Okay. So let's see what happens if we don't initialize. So I'm just keeping this place. Now, you see, so by default, it gave me zeros. So what calloc does is that one is for initialization. Oh, okay. Okay. So see, in when I'm using calloc, if I do this, I'm getting zeros. Okay. So what if I use malloc? Like similar, no initialization. I just want to print. Should be star. Okay, it doesn't matter anymore. Okay, now So in, yeah, so by default, it initializes these values to 0. Okay. So this yeah, so that's what I'm saying, that this one will actually give you so I just performed an operation uh, on this pointer. I mean, this pointer array as pointer block of memories. Uh, they are actually consecutive, so you can say this array. And what we did in the first code is that we manipulate it. We gave some values, we assigned some values in there, and in the second we did not assign any value. Okay. It's just this. There are like these are the two things. So it's like they are performing almost the same. Okay. It's just the syntax and the initialization. That's the difference actually. Okay. Now, now let's move to this heap algorithm. So, okay. So now we will write the code for this Huffman code. So it will be soon almost. So with this, I also like I can define it now, or I have to introduce it later. Okay, so let me just so first we define some. If you remember, like what are the steps of designing this Hoffman code? We need to count the frequencies, right? And what I said is that you have to like arrange the characters based on their frequencies in a sorted order, and we take the minimum two frequencies as the node in the Hoffman tree, and we introduce another node which is the sum of these two nodes, the frequency sum of the frequency of these two nodes, and we make it the parent of these two nodes. And we keep on repeating this step, and we add this node, that newly introduced node, in the frequency array, and we remove those two minimum nodes from there. Okay, so to maintain that two minimum arrays and inserting this one, inserting another new one, we use it, we do it using this data structure called heap, okay, min heap. So what do we need now? We have to create these nodes for this Hoffman tree, and we also have to create nodes for this what is called this heap. Okay, so first let's write this code for creating a Oh, yeah. Okay. So first I will create this, no, it's a Hoffman node. It's so first I'm writing this structure for this Hoffman node. It's a tree, it's a node of this Hoffman tree. And what are the properties of this node is that it should store a frequency, it should store a character, it should also must have a pointer to its children, right? So that's these are the things that will be contained inside this structure. Hmm. So structure is a variable that groups a different kind of variables together. Okay. Mm, So I need frequency. It's the frequency of the character, and I need character that there, and then I need pointer to its left child and right. So this is a Hoffman node of an Hoffman tree. Hoffman node is not good. Next, what we need is minimum heap. Okay, so now I will write the structure corresponding to this minimum heap. So what would be stored in here? The like what are the things you need in this min heap? So you need. So now I'm creating this min heap. So this consists of one is the number of nodes in the heap. I mean, right now, and because it's going to be manipulated throughout the time. I mean, as the algorithm goes, the elements will be deleted from this heap and elements would be inserted in that heap. So the size would be vary, okay, time to time. So there is a size factor in here. Okay. So I look at size and also like your heaps is depending on like there are finite number of entries. So you need to know the capacity of that heap. And it will create. Now I will what I do is that I'll get a pointer, okay, to the node of this Hopman. So I'm not storing the values directly. I'm storing them. So these values. So basically, this is storing this min heap nodes. These are just this stored the address of these Hoffman nodes. Okay, the values are stored in there. I'm not going to store any values inside these min heap nodes. These just points to the Hoffman node where the value is stored. Okay, because every entry in that uh, array, you can see it's a entry of this Hoffman node. Okay, time to time it varies. So when you build a min heap, you just it's sufficient to store the pointer of the minimum value node in a Hopman node. Okay, and you just go there and take the value from there and compare. Right? So it's so that's why we are storing a pointer in here to the Hopman node. Okay, there is no item or frequency. I mean, like frequency, mainly the frequency is not stored in here. Okay, no frequency value is stored here. There is a it stores an address to the pointer of sorry, it actually stores a pointer to the address of this Hopman node. Okay. So I define a pointer in Hop node. So pointer to the Hopman node, and this is a double pointer. So this one. Okay. So it is a pointer to the node of the Hopman. So, okay. Now we will write the structure, actually a function. It will be it's actually a function to create new nodes in the Hopman tree. So you can see that only leaves of the Hopman tree stores the characters. Others are not. Okay. So what I do is that I will write a function, this new node. This will get a node for this Hopman tree, and like every time you enter something, like you when we compute these frequencies, and we actually give frequencies directly, we don't compute. When we give those frequencies, we actually create a function of a Hopman tree of creating this Hopman tree, and whenever we insert some element in there, we use this create node to create new nodes in that tree. Okay, and we build it. Okay, and see why this is not sufficient for the Hopman node. Like why uh, I'm writing the create node function, because this is just a what I'm doing here is that this is the data type, right? So what I have defined here is a variable. Okay, so this variable stores a different kind of variables. So what I need to do now is that I have to use this variable to create some nodes in the tree. Okay, there would be nodes. Okay. So that's what I am going to do next. So this is a function that creates node in the Hopman tree. Node. So I'll name it new node. So the argument of this one is the item. So it stores the frequency and item, right? If you see a Hopman node, if you look at a Hopman node, it has this character, whatever character is stored in there. I mean, the leaf nodes. For the other nodes, see, there is no character. So that would be done by using dummy character. And this and the frequency. Okay. We need these two argument for this function. Now we define the node. So this is a pointer. Now we are defining a pointer. Create a pointer. So this is corresponding to the block of memory. I'm using malloc again. Uh, so this is a structure variable. That's why I am using struct. And this is the name of the, so okay, a struct and the type. So these, there are like two structures, two structure variables are here. Okay, so what I'm doing is doing here is that I am so if you look at the format of this malloc, it should be the name of the variable, pointer variable, and the data type star. Okay, so this is corresponding to the data type star. All right. So this Hoffman node is the basically the data type that we have using. It has this data type structure, so I am writing it in this way. Malloc again size of. So I defined a point. I defined a pointer. I mean, it will allocate some memory in there, and now I am storing values in there. So I am accessing this temp is a pointer. So I'm accessing its left child because it's a pointer of this type. In Hoff node, it has two pointers on its left and on its right. So what I'm doing is that on the left, I'm storing these null values first on both sides. Directly, you can write it in like 2 lines also. It doesn't matter. Uh, so I have set these null pointers on the two nodes, two children of it. And I also have to store a value in there. So if you see this Hoffman node type structure, it contains 3 components. This is done. Now we have to take care of this item. So I have to access this item and assign the item value in here that will be passed through the node, okay, through the argument of that function. I mean, passed through the node means that should be the value of that will be the character that's stored in the node. Okay, and next is frequency. So I have to access the frequency also. This, okay. So these are the component of this. This is like whenever you are entering a new node in here, you what it's a simple task. You just enter the character and the frequency of that character. It will create a node whose children are having null pointers, and it stores the character and its frequency. Okay. So this function will return this pointer to that node. Okay. All right. So this is the complementary nodes. We use it when we are creating new nodes for this supplementary. Next, we write this code for the min heap that we use. So the capacity of that tree is given. I mean, that is actually the number of the size of that array actually. Uh, so let's start. So this is again a pointer function. Like similarly, we will using this node. Okay. So it will create this. I'm now writing the function corresponding to creating a heap. Okay. So first, so the same. I create a pointer to this min heap. Okay. So I initialize the size. If you look at okay, if you look at this min heap, this is basically a type of this min heap node structure. Okay. So if you look at this min heap node structure, this one, what does it have? It has a cap size and a capacity and a pointer to the Hoffman node. Okay. So what I did is that here I initialize it to be size 0, and I'll pass the capacity same as the given one in the function. And I have to deal with this one, a pointer to the Hoffman node. So now I will assign this. Sorry, so min heap. So what it does is basically creates this size of like capacity means the number of frequencies basically. So it will create an array, a block of memories, uh, same as the size of the capacity. I mean the number of frequencies there. So it creates an array corresponding to this one. Okay, this argument. So this so this function should return me the mean heap. Okay. So this is the function to create the mean heap. Okay. Uh, Next, like we have to maintain the heap property, like I have discussed yesterday. So for that, we need like swapping of nodes and heapify. So I'm going to write those two functions right now. So this one is for swap. Sorry. Swap. Argument should be sorry. Yeah. So it's same like swapping. Sorry. Finally, the this is maps and next TCP5. Yeah. So uh, you observe that like this heap that we are using, we are using it through the Hoffman tree. Okay. So that's why we are always passing a pointer. Like when I'm saying swap nodes, it's basically I'm I'm passing this pointer to the Hopman node. Okay. I'm accessing values in there. I'm checking all the comparisons were based on the values stored at those nodes, but uh, the swapping that are done, it's done on the heap. I mean that array. It's not done on the tree itself, Hopman tree itself. Okay. So this is a point to note. Okay. All right. Next, right. If you recall, it's a binary tree, so it's kind of follow the two like left child it would be on 2i plus 1 and right child would be on 2i plus 2 index. Hmm. So this is the index in here, that index in the argument that I'm talking about. So it's based on the position, it will calculate its child and it will manipulate if there is like smaller, if the child is smaller than the parent or in any of the children is smaller than the parent, then it will swap. Okay. Uh, okay, so let's see. So now it's a comparison that I am talking about. That if the node is smaller, then you assign the value smallest to that one, and then you modify your tree. Okay, you'll see now. So what it means that if loop I'm going to write right now is here I am comparing the values stored at this left node and the right node, and I have assigned like you're finding the minimum of the both one. Okay, so okay, so tell me where is your doubt? Mm, okay, let me start from the beginning. Okay, uh, have you like Yes, I mean, I am describing like why we are doing these steps. Uh, these structures, we need these variables to like make those nodes, because these nodes are storing multiple things inside, right? What is the objective to do that? To do what? To do the coding? See, all this coding, whatever you do. Oh, now you're asking what to. This is Hoffman code. I have said it before in the last class, and I have said multiple times today also. I think you have missed. It's a Hoffman code. So we are trying to find this encoding of Hoffman code and also the decoding. So given a characters, we are trying to find the like we are trying to find a encoding for them so that we can compress the number of bits used, I mean the size, and also like after compression, we have to decode that one. So we are trying to do it efficiently. This is this Hoffman code algorithm. So if you are asking that right now, it's very difficult to understand. Then you don't know the problem, I guess. But I have discussed yesterday's class. I've discussed it thoroughly, I think, with an example. So I said in the last class that I will continue from there. That recap is not going to be possible today. So if you have any doubt regarding the construction of the code, then ask me that why. So let me explain again, then I will write the rest of the part. Uh, what are these steps? Like this one is for creating this. Yeah, I am doing that. So we have. No, I'll come to the code later. I mean, the rest of the code I will come later, because things are like going forward step by step, right? So this is the first one. So this idea of nodes and all, like this has this contains a lot of variables together. For example, like if you look at a node in a Hopman tree, so what are there? There is a character, and there is a frequency of that character, and it also should like store pointers to its children. So basically, there are three type of values we are interested in that should be stored inside a node of a Hoffman tree. And I said that I will use heap. So why we are needing this heap or any type of sorting? You can do it in any type of sorting also. You can use quick sort. Okay, there is no problem. Quick sort is inbuilt in there. Qsort is the command. Uh, I think it's not included in, maybe included in standard library. Uh, so you can use this quick sort also to write this code. That's very easy to implement, and like, but whenever you are trying to enter another like another frequency in there, because if you look at the Hoffman tree, what we are doing is that we take the minimum two frequency nodes, like minimum two frequencies in the array of this frequency of these characters, and we take the minimum two frequencies, and we make a node out of these two frequencies, and then we make another node, which is the parent of these two nodes, and that parent node has the frequency stored inside to be the sum of the two frequencies of its children. Right? So these values are stored in there. There are these children having this minimum value. So what you have to do is, okay. So now you can see that in the in heap, whatever the heap structure we have, or any sorting, any other sorting, like if you want to maintain the array to be sorted one, you have to like insert this another element in there, which is the some of these frequencies, because you have to remove those minimum two and you have to add this one. Okay, so you have to find its position in there, and you have to adjust your array accordingly, and you have to sort again to find the minimum two, and you have to do it again and again and again. Okay, so that would take a lot of time compared to this heap, because in heap you can do insertion and deletion in order n time or order log n time. So that's why heap is a better structure to use for this purpose, like where we are constantly modifying the tree, I mean the array, and constantly inserting an element and deleting one. So it's basically that's why heap is an useful structure in here. And basically, this is a priority queue that I have discussed last class. Uh, like I gave a name, like discussed a name, priority queue. So this priority queue works in like you want to like sort or arrange your elements based on their priorities, and the priorities is based on what you need, like either it is maximum or it is minimum. Okay. So this is a type of priority queue that we maintain in here through the heap. Okay, so basically we are maintaining two trees. One is the heap, another one is the hopman tree. Now in the heap, what we do is that we are not storing any values inside. We we are trying to, or like our intention is to not store any values or anything inside the node, just a pointer to the hopman tree nodes. Okay, because the entries in the heap, these are basically the entries corresponding to like at least corresponding to one of the entries in the hopman tree. Because you can see that characters, the frequency of the characters are the leaves of the hopman tree, and like there are some of the frequencies is the interim nodes of the tree. So you can always what we do is that we use these hopman tree nodes. We stored the frequency in there, we stored the character in there, and we access these nodes whenever we need to manipulate this min heap. And in the heap, we are actually storing a pointer to these nodes, these hopman tree nodes. Okay, so we are manipulating addresses in there in the min heap, and we are manipulating it looking at this hopman tree node. Okay, so multiple variables are combined together for a node. That's why we are using this structure where we can accommodate a lot of variables. So this is the data type structure, type of the variable that we want to define, and then this is the name of the variable, and here the collection inside the structure, what it stores. So for a hopman tree, I need the frequency, I need a character in there, and I need pointers to its children. One is left, one is right. And next, we create a node. So for heap also, we need this kind of structure. So this structure is corresponding to the heap. So here we need the size of the heap. I mean, like, because it's going to be modified throughout the code, like as the code passes, its size will decrease. Okay, so the size is the current size of that heap, and the capacity of that heap, that is like how many elements are there. It would be initialized in the beginning, and a pointer to the Hopman nodes. Okay, so this is a pointer to the Hopman node. So I'm not storing any values inside these heap nodes. Okay. Now we come to write a function that will create a new node. This will create a new node. Okay, new node where? New node in the Hopman tree. Okay, so now if you look at the Hopman tree node, what are the things it stores? It should store a value, I mean the frequency, and a character, right? So that's why I am passing these two things inside that function, and it's a pointer function. Okay. The star is corresponding to the pointer. So basically, this is actually a pointer. This new node is a pointer. Now, how it works? So its type is the Hopman node that we have defined. It's a pointer. And by declaring this one, so as you know that this is its data type. Okay, this whole thing is the data type. So it's the name of the variable. So as you know that malloc is working like data type star, malloc size of the data type. This is the thing in here. And now this is a pointer. So what we have to do is that we have to assign its left and right children. So I initialize it with null. If there are left and right, it will be assigned as left and right. So initially it's null, and the item that passes through in here, that would be stored inside, and the frequency. Okay, so where this item and frequency and all these things are stored, this is stored in the Hopman node. Okay, so this one. Okay, so this function will create a node, a pointer to the new node. Okay, that will point that Hopman tree node where there are values stored. One is item, one is frequency, and another is the pointer to its left and right child. Next, we started our code of creating the min heap. Why min heap is important is that by min heap, I know the frequency, which is the smallest one, and then I just have to extract that one. Okay, so it's a very easy task. That's why we are building this min heap structure, and it's so important that maintaining the heap property is also important. So this function will create this min heap, and in the argument, I have to pass through the what would be the size of that heap. So based on that, I have created this another pointer variable, and this is the type of variable. Okay, that's why it's there. So I'm defining some space again in the memory, in the blocks of memory, which is done through this dynamic memory allocation again. I'm using malloc. We declared this pointer. Okay, using this malloc. Now, where we declare this pointer, these pointers are corresponding to this min heap node. Okay, so that means that there are two components in here and a pointer to the Hopman tree node. So here I initialize the size to be 0 and the capacity to be the capacity of this minimum heap. And then we define this number of spaces that we require for that heap. And this is why we are multiplying it with the capacity. Min heap capacity means we are accessing to this capacity. If you look at this min heap node, min heap is this one. Okay, so this is the pointer. So this type is min heap node. So there would be this capacity factor also there, and this array of array. I mean this pointer to the Hoffman tree node. So that's why this is the data type. It's a Hoffman tree node because we are using this array, and array is a Hoffman tree node. If you look at this definition of this pointer. So since it's a Hoffman tree node, I have to use that Hoffman tree node variable in here. Same definition as malloc. And here we just multiply it with the capacity, the number of spaces that we need for that. So that would return me the min heap. Now we are writing the function to maintain the heap property. Okay, so this is a simple swap function. And like as you know that we are not doing the operation. I mean, like every time we have to compare or access the values of these two nodes, we have to look at the supplementary nodes. Okay, so that's why this swap is based on the supplementary nodes. These are the pointers to the supplementary nodes. Okay, so and the inside code is very simple, like usual swap that we have. Okay. Now, what I'm writing next is the sorry is the it's the heapify that maintains the heap property. So for the heap property, we have to like find the minimum index that should be like all the parent, or like a parent would always be minimum than its children, right? The value of the minimum value of the parent should be smaller than the both of its children, right? So at a certain time, like if you are at a certain node, so say like node index I. So at that node, index I, if you look at it's a binary tree. So in the binary tree, if you look at the ith node, its children is at the 2ith node and 2i plus 1 and 2i plus 2 nodes, right? It's a property of binary tree. If you look at the binary tree, you will see. So now we have to look at these indexes and check whether the values are smaller or greater than the root node. Root node means the parent node. So that's why this left is the index of this one. So and we are accessing to the min heap value that's stored in there. And also now we are comparing the values. So values are stored in where? It's stored in array. Right? So this is array. So this array is a pointer to the Hoffman code, right? And by left, writing left, what I'm trying to access, I'm trying to access to the node of to the left child of that node. Okay. So this left child and what are you looking at? We are looking at its frequency. Okay. So this frequency, if it is smaller, than the frequency of the root, And the same thing for the right. Okay. So we find the minimum of 2, and if so we assign that one as our. So what we do in here, we are trying to find like which one is the smallest one. We assign that one as our uh, root. Hmm. Okay. So if it is the left one, then that's the left one. Then we assign that to be the smallest. If it is the right one, then we assign that to be the smallest one. Okay. So if now it's the heapify property that are going to work. So if it's not, sorry, it's already defined. Hmm. I'll call the heapify again recursive. So this is the heapify. So if you look at the you comment things like comment on every line is very difficult actually. And I have to, since it's a very actually it's a long code, and I get it that it's hard to understand. Uh, what I'm suggesting is that you should like break it into parts. I am writing the names in such a way that it defines like what part we want to do. It's better like if you are, let's say when we are working on this heapify function. So for like heapify, as we have seen in the class, that it what it does is that it swap values. Right? Like if an entry, so I have to maintain the binary tree property as well as the heap property also. So for that, I have to check like if the new entry is smaller than the others or not, and then based on that, I adjust its position. Okay, so I can, okay, so, but I mean, it's written on the name actually. This what it does. It's written on the name of these functions. That's why I'm not writing, because it doesn't make any sense of commenting uh, on like here. But like commenting on each step is possible, but it will take too much time. That's why I'm skipping commenting on like each step, like what am I doing in here. So if you look at this function, so it you just follow the names. Okay, name of this variables, name of this function. It says what it does. This one is swapping for a swap function that we write. This one is doing the heapify. Now, how the heapify is done, that's the algorithm. Okay. So if you follow the heapify algorithm, I have not discussed the algorithm in details, so in the class. But you guys said that you know heap, so I assume that. I just gave a recap, short recap, and I hope that you guys have gone through that one. Uh, it's just using the binary tree properties in here, and if you recall, the values are stored in this. And we are comparing the frequencies, and these frequencies are stored in this Hopman tree nodes, and this heap, in the heap, the nodes are basically pointing to the Hopman tree node. So every time I'm calling a node of that heap, I'm basically calling this one, this array, which is basically a pointer to the Hopman tree node, and using that pointer, I'm reaching to the corresponding node. And this integers, like smallest index and its children, this is the property of the binary tree. Okay, so like how this heapify works, or how this Hopman code works, is that I will, okay, when I will complete it, you will see that all the things are done inside a function. Hmm. There is a single function that will do the uh, Hopman code. Okay, so that Hopman code function that will call another function, which is the Hopman tree. And when we try to build this Hopman tree, we will be needing this some other functions, and we will use these heaps also. And when we are using that other function, like there is a like this other function is basically a build heap, create and build heap. So that create and build heap, I mean, it will create a heap, as well as it actually it creates and modify the structure such that it will maintain the property of a heap. Okay, so I will call that function, and that function has this frequency and item. I mean the character item, and certain, and then the size of that array. I mean the number of characters. Okay, so that function would require this what this function called this heapify. Okay, so heapify is a recursive function. We have to like, so you want to so whenever you are inserting one node, you what are you checking? You are checking that is it the is it smaller than the available space. Like if everything is filled, so for example, like if your index is, let's say, suppose you have entered like second node, okay. If your index is 2, so you set the smallest to be 2 and you look at next two spaces. Now you are checking that, okay, if that value is smaller than the smaller than its left child, if it is, then this value would be, then I have to find the which one is smaller. So I find, let's say it's the left one is smaller, then this will not execute it directly, left one will go. So if that does not match to your index, that means it's a wrong position, right? Because if it is 2 and the smaller comes at 4, then that means that your whatever you are inserting right now, this is not a heap. The structure is break, because in this array, if you look at this array, all the elements that are smaller than all the elements that will appear, like it's kind of a sorted array. Okay, so the parent should be smaller than the children. So that means the index, I mean, whatever stored inside this index value, index position, that should not be, that frequency, that should not be greater than the frequency of its children, right? Otherwise, the property will be violated. So that's why we are looking at this positions, that what is the smallest position, life, from the current index. If it is on the left, if it is on the right, then it's not the smallest one. Okay. So that's why it's, if it is not equal to the index, if the smallest doesn't come at that index itself, that means the position is not correct. That's why we are trying to do this swap, and we call this CP5 repeatedly. So this function does this thing. Okay. So is it clear, like what is this function is doing and how it's operating? So here I am finding which one is the smallest with respect to this current position, which children is smallest one, or itself is smallest one or not. If it is not, then we are trying to swap these values. Okay. So this is the heapify. Is it? Okay, fine. So up to now, is there anything else? Any other question? I think it's clear why we are doing this heapify. I will be writing the rest of the codes, but heapify is fine, right? So it will help you to maintain the heap properties. Okay. Now we were moving to the next part of the code, which is this okay. So we need also, like if you look at the heap structure, there will be like extract minimum, which is basically extracting the root. That function I will write now. So there will be like 3 or 4 more functions based on heap. One is this insertion in the heap, and one is the extract minimum. I mean, extract the minimum from the heap. These two, and then there is this build heap function, and then there is this create and build minimum heaps. Okay, so these are the functions that we need, and this is basically, you will find it in the heap sort also. If you look at the heap sort code, or if you want to try even like, yeah, it's also if you want to do heap sort, you will exactly have to implement these kind of things. Okay, just you can directly use the array instead of pointer to a certain node. Okay. Or like you can use pointers, but you don't have to point it towards another node. You can just point it to an array. Okay. So this part is very similar with the heap sort algorithm. Okay. All right. So see, now what we do is that, if you recall, like every time I am reducing the size of the heap, right? Like size of the heap means that a frequency array. So two frequencies, two minimum will be taken as nodes, and they will be taken out of that array, and one frequency is added, right? So how long will it continue till we reach to the root? I mean, that would be the root of the Hopman tree, right? So I have to perform this whole operation till my Hopman tree. I mean, till my heap. I mean, if you look at this array as a heap, we are looking at that array as a heap actually. So that heap size should be equal to 1, right? So till this heap size is 1, we have to run this algorithm. Like we have to extract this two minimum out of this heap. We have to insert another frequency in there, which is another node, and we have to maintain the heap property from there. And we keep on like extracting two minimum and inserting another element till there is only single element left, right? And we include that one as our root. So we have to perform this operation. So this implying that there should be a while loop uh, that runs. So how long I should run it? Till the size is 1. Okay. So to do that, I'm writing just one function which will guarantee that, okay, if it which will tell me that whether the size is equal to 1 or not. So that will be used to judge the to be inside to satisfy the argument in the while loop when we use that while loop. Okay. So this function is the size 1. Structure. I'm passing this heap in there. Okay. So it will return whether the size is equal to 1 or not. Heap size equal. So if it is 1, it will return. Yes. So this is an identifier. Now we are writing the extract minimum. Okay. Okay. Heap size 1. Now we are writing this function for extracting the minimum value. Extract. Okay. So we're writing this function. So in that argument, we pass the minimum heap because we just need to extract the minimum out of this heap. So in the argument, we just have to pass the heap only. What it does is that I have to so why this minimum array 0? Uh, since it's a heap, it's a min heap. Min heap means the root will be the minimum value, right? So where should I look at then for the minimum? I have to look at the heap, the top of the heap. Okay. So and the top of the heap is at what position? At 0th position. So I have to. So this pointer is pointing to the location where the like the smallest element is there. That means the 0th element. I mean the first element of that array. Okay. And then okay. And we have to decrease the size of the heap because we have extracted that one. So this means that size is reduced by -1. That's done in here. And then we have to call heapify to make it. Mhm. So we have to. So this is nothing. We have taken the minimum out. So this is the minimum value from minimum. Sorry, this is the pointer to the minimum frequency. And when we extract that one, this we have to maintain the size. So we reduce the size of that array by -1. Okay. And we also like have to change the size of that array also. So this one, and for after that, we have to maintain the heap property. That's why we call heapify in here. Okay. So this is the function. This will return. Okay. So this temp will store the minimum value in here. And okay, so after that, like if it is storing the value of 0, then what we are doing is that we are assigning a value in there. And the last value. It's basically the extract min algorithm in uh, priority queue. You can check, although like it's very, like you can understand it from here. We have to uh, like when the 0 is assigned, the 0th position is emptied. Okay, we assign some other uh, node as a as our root node A0, and then we modify it to the heap node using heapify at that 0th node. Okay. So this is what is done in here, and for that we are using this n minus 1. I mean, if the size is n, it's n minus 1th position element to be the root, and then we use the heapify to adjust it. Okay. So this is the structure. Okay. Oh, I mean, this is done for the binary tree property also. You can check. If you read heap, you will see. Okay, this is done in accordance to maintain the binary tree property also. Okay. Next is the insertion. So in this function, I am passing one argument as the heap node, another one is from the Hopman node. Uh, why I'm doing this is that we are trying to insert the frequency that would be and that will arise when we sum the two minimum frequencies. Okay. So this size. Okay. So what is going on in here is that so whenever you try to insert something in the heap, first you have to increase the size. Okay. Now for the existing heap, like here, what I'm looking at the like you have increased the size of the heap, right? Now you are looking at the original heap that you have, like the like suppose you enter an element and heap is of already of length 5. You are entering one element, so current length is 6, but now I'm looking at this 5 length, the initial 5 length heap. What am I trying to do is trying to find the position for this element that's inserted. Okay. So I'm checking the frequency of like that one, and it's actually the parents of that one, I minus 1 by 2. If you look at that, it's coming from the parent, and here I'm adjusting that one. Okay, so I'm finding the place for that node, and whenever I whatever place I come up with, I assign that one to be our this node. Okay, so this is the insertion. Now we write the function to corresponding to building the heap. Okay, so now it's the build heap. So this is the heap size. Okay, so this will build the heap. All right. Now, now we proceed to build the Hopman tree. So in the Hopman tree, So now, if you recall that the characters are on the leaf, so whatever, like whichever node is a non-leaf node, I have to differentiate between this leaf nodes and non-leaf nodes. So that I write a function that will differentiate between these two nodes. Okay. Uh, this one is corresponding to like whether it's the left child or right child or the root. Okay. So it's leaf or not. This will just return. So we'll return that on. So what this logic says is that if it is this function will return positive. If it is yeah. So if it is not the left child, I mean if it is either the left child or the right child. Okay. So if both are not, then it will return true. Okay. If one of them is yes, then it will return. Well, it's actually very long code. Yeah. Uh, I mean, because we have to do this sorting also. Hmm. This creating this tree uh, and also maintain the sorted order. That makes this code a very lengthy one. There is a shortcut for this one that I have told before writing this code today. I told you that you can use quicksort directly. Hmm. You have to like you can do the Hopman. You can make the Hopman tree instead of using the heap. You can use the quicksort, which is done by qsort right away. But you have to use this quicksort repeatedly. Hmm. Whenever you are like you have to take an array. So you have to declare an array first. Okay, based on the frequencies. The problem is with the size. So even if you declare a dynamic array, like using the malloc or calloc, if you define some memory allocation for that one, you have to apply quick sort in there. Then you have to remove that element, remove the minimum 2 elements from there. That would be based on their indices. And then you have to insert another element. So this insertion is a difficult process. Okay, because whenever you are inserting, it may not be like you cannot insert directly in the beginning because it may not be the, since the array is already sorted, it may not be the smaller minimum number. Okay, so you cannot enter in the beginning, you cannot enter in the end, you cannot, like, you have to find its correct position. That would make you like order n number of searches. So that's a like lengthy process. This code is very lengthy, but in complexity wise, it's very helpful. It's a very long code. Yes, it's still I have not completed, like I have not built the tree yet. I have to build the tree. I have to what are the things left? Yeah, I have to build the tree. Then I have to write the function. For building the tree, I need 2 more functions. This is really too long, but I cannot help. It's a problem that's making it difficult. Okay. So next is sorry. So this command will create the min heap, this function. If you recall, we have already written a function that gets min heap of the given size. So these arguments, these are from the user input, the frequencies and all. This will create the min heap, and now we'll call, like, we will insert new nodes, and we will call the build heap that we have used right now. So just about this one. Okay, so that will create and build this heap. So this will store what? New node. And new node, if you recall, new node has frequency of this. New node has arguments of this frequency and corresponding item. Okay. This to, and then size is the given size, and we use the build argument is just the heap. Yeah. And this function will return them. All right. Next is now we are almost like ready to build the Hoffman tree. And so this function, the next function will build the Hoffman tree. And after that, I will write a function to print the array and to print the Hoffman codes. Okay. So this next function is the build Hoffman tree. So the argument is 7. Pointer to the left. Right. So what it does is that I'm creating this left pointer to the left node, pointer to the right node, pointer to the top node. And now I will call this build heap, which will build the heap corresponding to these nodes. And we'll pass the same thing. Now that while loop I talked about, that if it is not of size 1, it's also, if it is not of size 1, and this function has this multiple. So if it is not 1, then we apply that. So this is that we have extracting the 2 minimum out of it, making the left turn to be the smallest one. And you can alter change, but it's like it doesn't matter. So we extract these 2 elements out of this heap. And now we create a node. Here we use again the new node. Now see, this node has no character stored in here. So we play this dummy character in here. So now, and this node, the frequency of this node would be the sum of these 2 nodes. So adding these 2. frequencies. Okay. So and this just set the pointers of the route to the childs. And after that, I have to insert this new node into the heap. Okay. So where should I insert in heap? I'm inserting this node. Okay. So this is the part. It's actually a pointer. So in the standard notion, when we are using this normal function names, so these and these are like that functions. So those are what I can say. Those are not actually any pointer to uh, some other I should say that is not a pointer to some other variable. For here, like you can see that uh, in this part, like when we are using this star function, so this means star root function before function star root. So this star function is basically a pointer. It's denoting it's actually a type, and it's pointing towards this nodes of this Hopman tree. Okay, and this star root or star right or star left, any star is a pointer. Okay, this pointer actually has the address of that location. Okay, where the value is stored corresponding to this nodes, like for root is basically this one. The star root is basically where the value corresponding to the root is stored. Okay, so it name it root because we are looking at the root, but it could be like anything. You can name it anything. The name doesn't matter. The star refers to the location because this Hopman node is the place where these values are where I'm looking at. So this star root is basically a pointer to this Hopman node where we have stored the value of this of this. I mean, this is a so this one is actually a data type that we have defined in structure. So this data type, and this is the name of the variable, and this is a pointer variable. Pointer variables does what? It actually points to some address where the value is stored. So this root star root is pointing towards a value where the location of that root value is stored, which is basically checking whether it's the left it's has the left pointer or the right pointer or not. So this one is like when we are doing this, if this root is a left, let's say it's not a root node, okay, it's a leaf node, then what will happen? So if you look at this min node, Hoffman node and pointer corresponding to this Hoffman node. This represents, if you look at this Hoffman node, where is the Hoffman node here? It has two pointers on its left, on its right. Okay. So if it is not the root node, then this pointer should be null. Okay. So both of them, both of them should be null. Okay. So if, so when you are checking, we are checking that, okay, I'm checking that, checking this root pointer, and I'm checking whether it has this left pointer or the right pointer or not. And if the both pointers are absent, which is done in here, that means that this is our root. This is a leaf node. Okay. Otherwise, it would be a root node, and in this function will return nothing. Okay. So this star root is actually a pointer towards the Hoffman node, where we have like this where there are like two pointers are there to its left and right child, and frequency and item and the character is stored inside. So this is the thing that we are looking at here. And star function is basically the pointer function. Okay. Let me complete this one, then I will discuss thoroughly. Session. Okay, it's not completed. Oh, sorry. This while loop should continue. This I have to keep on adding the elements. So it will return. Now we need one thing. Next codes are just to, I'm writing this one to print the array, and then the next code would be for printing the Hoffman codes. I mean, just the decoding part. So, So this is corresponding to the Hoffman node that we wanted to print. Okay. So this function has this root and the array, and I have to traverse from the root. And whenever I take left, I have to assign 0. Whenever I'm taking right, I have to assign 1. So that's the logic in here. So this is just the printing, and this is the it will combine all the functions together. Have to set a value in now. So Okay. Okay. Fine. Rest is the main function. Now let's see the questions. So, what are the questions? Let me check about secure. Okay. So your first question is why we are using star before the function star root. Okay. Okay. So this star root is right. Oh, is there 152? Oh, yes, yes. Okay. Thank you. Okay. So this someone questioned that about this star functions that we are using in here. Uh, this star create min heap or star create star some other. There are some other star functions also. What it does is that there are like functions actually what when you write a block of code, right? So there are some instructions in there in the function that and it will perform a particular task. Hmm. So that's what our usual functions are. Okay. Now these pointers, like for these star functions, for example, one is talking about this. I think Hopman code has one star build Hopman tree. Yeah, star build Hopman tree. This one, right? So this is a pointer actually. Hmm. This is a pointer to what? To which this actually the pointer to this function. Uh, so what we do is that there are two type of things in there. I think in functions, if you are familiar with that pass by value, and then there is uh, passed as an reference. And what it does is that when we store this function pointers, it allows us to use this as a argument of other functions. Okay, so this flexibility is we can get using these star pointer functions, and this is the main difference basically between a function and a pointer function like this one. Okay, so what it does actually, what is the meaning of this function? If we look at this function, this basically carries this. If you look at a hop and tree node, it has a character, it has a frequency, and it has the pointer to the left and right child. Okay. And whenever we're trying to build the tree, I have to know the height of the tree. I mean, that size, number of nodes in there, and the things that I need to store inside that tree. Now, this tree is like, you cannot like a single node cannot define that tree, right? It's a collection of nodes in there. Okay. So what it does is that it's storing the addresses. Okay, that this is corresponding to, these nodes are corresponding to the tree. So that's why we are using the pointers to these nodes. Okay, where the where we are. So if you look at this, what is it returning? It's returning the mean heap value. Okay, this function, this Hopman tree. So this, what is happening in there is that we are this function is pointing some nodes as this Hopman tree nodes. Okay, and each node will be a structure of the form of this Hopman node. Okay, so now see it's not represented by a single structure or something. So that's why it's we are trying to point at the locations where the nodes are stored. Okay, so that's why this pointer is used in here. Okay, so this is a pointer function. This is different than usual functions. And whenever we are using star left, star right, star root, or whatever, this is a pointer to the corresponding variable. For example, here it's start min hof node. That means it's looking at the Hofmann nodes. It's a pointer to this type of variables. Okay, and all these are the variables. These are the name of the variables actually, and this is the type of the variable. Okay, so which type, that's maintained, that's denoted by this one, and the name of the variable is denoted by this one. Now, whenever we are trying to access to these variables, what we are getting is that it will refer us to the corresponding position. Okay, so that's what we are getting through this star value, this star pointer, or I mean star root or star function. It's basically pointing towards where the root is stored, where the function is stored, etc. Okay. So I have discussed previously, I think, till this heap one, build heap. Then we write this code to build the tree and build Hopman tree. So this Hopman tree is built through this following steps that we have defined. Like for the tree, you need 2 pointers to the left and right, and another to the node. Like if you look at the node in intermediate node, it should have a pointer to the children as well as a pointer to the top. So that's what is happening in here. We have defined 3 pointers, and we also have to build a heap corresponding to this one. So corresponding to this one means we have to like maintain the heap property. We have to maintain the frequency array, right? So that's why we are using that heap. And what we are doing in here is that we extract the 2 minimums, and it's a step of building that tree. So we extract the 2 minimum, and we create another node. We insert that node in the heap again, and we keep on doing this until until the size is 1, which is maintained by this one, that the heap size is 1, and this one loop will continue till that, and then after that it will terminate, and we have the Hopman tree, and this function, this whole function, this will return the top of the heap, which is left after that one, after the process. Okay, so this one is that next is this is print array nothing, and this is the like traversing the tree from the root to the leaf. So what this says is that you go to the root, from the root you go to the left. If you go to the left, it should be 0, so you get 0, and then you go recursively. Okay. Similarly, if you are going to the right, you take 1. So this will corresponding to that one, and if it is a leaf, then you halt. Okay, so this is the thing. Okay, Next is that uh, okay. Next is this Hoffman code, which is actually a combination of all these codes. It's just simple. I have to pass this to build the Hoffman tree. So we are building the Hoffman tree in here, name that variable as root, and we have initialized these values. And then we just, after building the Hoffman tree, we just have to traverse the Hoffman tree, which is done by this Hoffman code. Uh, okay. 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 So now let's see. I hope that there is no mistake in there. Otherwise, it would be. A, B, C, D. Oh, it's correct. Uh, 9. Oh, right. It's a bad mistake. There should be semicolon which end this definition. I did not. Failed due to following errors. 23. The return was not declared in the scope. No, 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 no. Oh, return. Sorry. You are in this type of errors. and not convert. Okay. Yeah, I saw. So bad mistake. Oh, it's not pointed. Sorry, it should be the value for this option. Okay, size has not been declared. Oh, 116. 116. Oh, 61. Code. Yeah. Okay, finally. So this is the code. Oh, okay. Yeah, I think it's correct. You can check. It's a very long code. Yes. It it take it takes time actually to go through the whole thing. It's but it's a nature of this code actually. If you want to like shorter code, I already tell that you can use the quick sort, but that will just increase the complexity. So yes, I'm going to paste. What I would suggest is that like since we are dealing with these pointers and all these nodes and all, uh, you guys at least try to uh, play with these pointers and all such that you can be familiar with this type of functions and this type of structures also. Because like if we are dealing with the graph, let's say graph algorithms, for example, I think I don't know whether it's covered in your class or not, like this Kruskal algorithm, Prim's algorithm, because they are greedy algorithms. So these greedy algorithms or any other graph algorithms, if we want to deal with them, we have to deal with these nodes. And whenever we try to define any graph or something, we have to define these structures responding to these nodes and then using them repeatedly, using these pointer functions also, which actually points to some location where the values are, where we are executing this function. And you can pass it inside directly. Okay. So that's the benefit of this type of things. Mm. Okay, fine. I'm going to paste it. Okay, fine. Please go through the code thoroughly, taking your time, and try to uh, like do the coding for a little bit where you're using these kind of functions, these functions of pointers or this using these pointers. Because if we are moving to C++, yet we need to use these pointers and functions. Okay. Okay. So thank you for today. That's it for today. It's a very long code, and we'll see you in the next class. Oh, it's not like memorize all these things. I have written it down. I cannot do it uh, directly from my memory. I did it like before, and then I write it down. You cannot like just one go develop this kind of code. It takes time. It takes a lot of time because you have to think about the thorough process, like what are the steps. So the breaking down of this code is that I take the heap one because I know that this many steps I have to do for the heap sort. I mean, heap sort is the heap sort of priority queue we are using in here. So this many functions I need for that one. So this is the finalize this many things I need, and then breaking down the Hopman tree actually. That in the Hopman tree you have to build the nodes. So to build the tree, you have to build the nodes. You have to create this heap also simultaneously, and you have to maintain the structures of the heap. So these are the key factors corresponding to the functions that we have created throughout this code, and we created based on this actually these thoughts that this many things I need for heap, and in the Hopman tree, these are the properties that are going to be held. So I have to satisfy these properties. So this kind of functions I need, this kind of functions I need, and that's why that's how I categorize this function. If you look at the name of these functions, you will see that these are the names corresponding to what are the functions they are performing. So that's it. There is no memorization. You cannot memorize this kind of codes. Don't try to memorize also. Just try to understand these things. This kind of long codes, I mean, it might not come in your exams or something, but if you write it in one go, that needs a very, very high efficiency of coding. Like if you should be very good at coding, if you can write it at one go. Yes, it's like you first go through the heap sort or priority queue algorithms. You see the structure in there, and you understand that okay, I have to use it now in this case, and how you are using it is based on the algorithm. Okay, so that's it. Okay, thank you everyone. I'm closing the screen. Okay, so we'll see you guys in the next class. Okay, stopping the recording also.